Hi everyone, we're the CubeSat Magnetorquer control team, part of the UW CubeSat team, which is made up of undergrads, grads, and doctoral students. Why is our stuff important? Well, has this ever happened to you? Oh no, my imaging satellite is out of position relative to the next target, and our reaction wheels won't spin any faster. Well, do we have a solution for you? Normally, we'd spin up these here reaction wheels in one direction, and due to the conservation of angular momentum, the rest of the satellite would receive the same momentum spinning in the opposite direction. Combining the torque from wheels along each of the three spatial axes allows satellites to point in whatever direction our clients want. The reaction wheels have to keep imparting and taking away angular momentum to keep pointing toward various targets while fighting off disturbances like the effects of orbital decay. But now, aw shucks, these reaction wheels are maxed out. It sure would be nice to have something to push against other than the craft itself, allowing us to slow down these reaction wheels without putting all that stored momentum back into the satellite. Well, how about Earth's magnetic field? That's right, with our not at all patented Magnetorquer technology, you can run an electrical current through a loop of wire, turning that wire into a mini magnet that will try to align itself with the Earth's magnetic field. In doing so, the loop of wire exerts a torque on the spacecraft, which can be countered by the torque exerted on the craft by decelerating the reaction wheels so they're no longer at their maximum speed. The final product consists of magnetorquers embedded on the satellite's sides, a specially designed circuit board that takes signals from the satellite's main computer and translates them into electrical currents to flow through each magnetorquer, and finally a special program on the main computer that allocates what signals and currents need to go to what magnetorquer to best desaturate the reaction wheels. This is our final design, complete with evenly spaced chips to disperse heat, along with connectors to each magnetorquer optimized for their relative positions on the satellite. Our circuit has to be ready to survive the harsh conditions of launch and space. We are following the qualification testing outlined in the CubeSat design specification document by Cal Poly. Our circuit will be subjected to a series of tests that will replicate the loads on the circuit as it orbits. We will be able to see how the circuit degrades over time, making sure that it will survive the mission and then some. The circuit will also be subjected to a series of tests that will heat the board to 175 degrees Celsius and down to negative 55 degrees repeatedly, mimicking the same temperature cycle our satellite will experience as it zooms around the world every hour and a half. We will also subject the board to the same vacuum it will experience in low Earth orbit. Finally, we'll need to make sure that the board will not only survive space, but also the violent rocket ride to get there. We have to verify that vibrational modes are above 100 Hz, since the most powerful launch vibrations lie under 100 Hz by exposing the board to frequencies from 0 to 2000 Hz. Craft that don't have our technology hooked up will max out their reaction wheel RPM and get stuck looking at one location on Earth per orbit, and there's a 70% chance that location's going to be water. You don't want your mission to fail, and neither do we. Call now for just 3 easy payments of $19.99. You'll get our full Magnetorquer control scheme outfitted on a satellite of your choice, and we'll throw in one of our nice mission patches for you.